Okay, so Riddhi and Max are going to speak next. I'm going to give the mic to Siva. You had an announcement. You want to do it now? Oh, and then the talk. That's okay. So then, Riddhi, please go ahead.
All right. Yeah, thanks, Frank. Yeah, so we're going to continue talking about voter models today. So as yesterday, we'll have a couple of people presented. Just to give you a brief overview of what will be done today. So we are going to introduce, by the way, I apologize to Raghavendra because I promised simulations today, but they're not ready. So hopefully they'll be ready on Thursday. So apologies for that. But so we'll talk a bit of mathematical tools that one uses to study voter model. So Max will start with the very basic tool, which is the time reversal duality for voter model on static graphs. So this is not for the dynamic setup, but for the static graph, the classic ones. But maybe we'll see at some point how that can be adapted. And then this will show us how it is to study voter model. It's very important to study random walks for static graphs at least. And then for the second part of today's talk, Deepening will talk a little bit about how to study random walks in terms of eigenvalues for random walks on Shreni graphs and random graphs in general. Okay, Max, over to you.
Thank you. Okay, so as mentioned, I will start with, I guess, the basic tool for analyzing voter models for static graphs, which is the notion of duality to coalescing random walks, which we will be able to just read off from a given graphical representation. So just so everyone is on the same page, yesterday the graph was evolving, right? So today we just fix a finite connected graph, and we will call a continuous time voter model on G. We will define as a Markov process on the state space 0, 1. So again, with binary opinions. 0, 1, okay, red, yellow, however you want to interpret it. And at rate 1, every vertex V chooses to adapt the opinion of one of its neighbors. So very classical voter model, static graphs, no change of edges, no nothing. This is the very basic model, right? So again, just to show you an image, the exponential clock with rate 1 in the vertex that I've circled there is ringing, and then it uniformly chooses one neighbor. And in this case, it will be the left one there, and then it chooses to adapt their opinion. This is the very classical voter model, I guess everyone is familiar with. And notice that the only absorbing states in this scenario are the configuration where every opinion is 1, or every opinion is equally to 0. And we define this is what we call consensus, right? So yesterday we saw that, I mean, in some sense it's similar because we don't have discordant edges here since we are connected. This only happens if we have equally 1 or equally 0 distribution. And in the evolving process, we saw yesterday that there are also states where both opinions survive, but there's no discordant edges. So in this case, this will only be true if we have consensus, and we define the consensus time as the infimum over all time points where, yeah, consensus is reached. Okay, a very classical way to construct these interacting particle systems is the graphical construction, where you consider the following graph. So on the x-axis, you have the vertices of the graph, and then on the y-axis, you have real line, positive real line that indicates time. And then for every vertex, you have a Poisson process with intensity 1. And then if there is some time point for some vertex in that Poisson process, you choose uniformly one of the other vertices in the neighborhood of that vertex, and you draw an arrow v prime t bar to v t bar to indicate that at time t bar, the vertex v chose to adapt the opinion of v prime. And this is how it's going to look, the upper right. So these are going to be the arrows, right? This is time, and at t1, 2 chooses to adapt the opinion of 1. At t2, 3 chooses to adapt the opinion of 2. And then at t3, 4 chooses to adapt the opinion of 5. And this is how this is how we can read off the process from this graphical construction, right? So we initialize with the graph, which is the same graph that we have just started our initial example with. So you initialize at t1, as I said, 2 chooses to adapt the opinion of 1. So it becomes yellow, it becomes 0, however you want to call it. And then at t2, we see, okay, 3 adopts the opinion of 2, so it also becomes yellow. And then notice that here we have reached consensus already. So the next time something happens, I mean, the Poisson process still keeps running, but we won't observe any change in the graph anymore because we have reached consensus. So every influence will just be you will adapt the same opinion that you already have if you choose to adapt the opinion of one of your neighbors. And then what people do, if you fix a time horizon, you sort of trace back the origin of the opinion, right? So what you do is you define for any vertex v, you can define here it's 3. You can define the following process that is initialized in v, so at time 0 it is in v, zeta 0 is v. And then if at time t0 minus t, so it runs backwards in time, right? So this is this time reversal. There is an arrow pointing at zeta t minus, then we will perform a jump in opposite direction of the arrow. So basically exactly what we're doing is just tracing back the opinion backwards in time, right? So we start at time 0, which again, it's running backwards in time now. We start in 3, then we trace back, we follow back this arrow, follow down that line, and then we see, okay, the origin of the opinion of 3 at time t0 is the opinion of 1 at time t0 is the opinion of 1 at time t equals 0. So obviously, okay, this is a rate 1 random walk. We just walk at rate 1 and uniformly choose a neighbor to walk over to. Of course, now this is coupled to the auto model forwards in time process. And this is what I just said. We can read off the opinion at time t0 as the opinion at time 0 of the position of that walker at time t0. So this is the first sort of duality relation for a single vertex. And then to insert this into a sort of more global picture, what one does is one gets a system of coalescing random walks, which is the title here, and then what you do is you define one of those processes for every vertex in the graph. You start with one vertex with one walker at every given vertex, and then you perform such a random walk. Again, this is time reverse, so you have to have a fixed time horizon. You perform such a random walk backwards in time, and if 2 walkers meet, for example, the first time this happens is here, the 4, right, will follow back the arrow. And it will switch its position to 5, but this 5 is already occupied by the walker started there. So if 2 walkers meet, they coalesce. And this is the way you trace back the opinion of the whole system. And then if we let AT be the set, so the set of all V such that there exists a walker at that position, so the set of all positions, then you can see that consensus on the whole system at time t0 is essentially just consensus on the initial configuration for all the positions that are still alive at t0. Especially if we define the coalescence time to be the first time where all the walkers have coalesced down to just one walker, we have that consensus is definitely reached, right? Because then it will definitely be constant on this one position. So you have consensus, tau consensus is smaller or equal than the coalescence time, right? So as I mentioned, this is a very classical tool to prove stuff for the water model. For example, in 1989, this was done for the water model consensus time in the d-dimensional torus. I guess that's a very classical reference, and it heavily relies on the duality between the coalescing random walks and the voter model to observe bounds on the order of the consensus time. That, of course, depends also on the dimension of the torus. And then something that is maybe more towards what our group wants to do is a paper that recently came out by Luca Avena, Baldasso, Hazra, the Hollander, and Quattrupani, which is the voter model on random regular graph with random rewiring. So they also have a rewiring dynamic, but it's in a one-way feedback sense. So you don't have this interplay of rewiring and voter model moves, but the rewiring is not influenced by the configuration of the model. And there, a very similar duality. I mean, it's not as graphical because you have to reverse the graph process, but a very similar duality relation is used to observe convergence to the right Fisher diffusion of the opinion density. And it's also used, I mean, they observe the exact meeting time of the random walk to observe the exact diffusion constant for the right Fisher. So this gives hope that stuff also works in a more dynamic, in a dynamic setup, right? Because, okay, the Cox paper, it's still a static graph. Here we have a one-way feedback. And then, yeah, I will try to sort of turn over to our setting and try to convince you that that duality is also playing a role there. So we have this paper by Professor Basu and Sly on the evolving voter model on dense random graphs, where we have the model that Elena pointed out yesterday, just initialized at the Erdos-Renyi n1/2 graph. And then, okay, just to recall, in our model, we choose a discordant edge. With probability beta over n, we perform a voter model step, while with probability 1 minus beta over n, rewiring is performed. This is, and then you just rewire to any, oh, this is not rewired to random, it's supposed to be, I think. So you just rewire to anyone. And then if you, now what we are considering, or where the duality comes into play, is a sort of a time-delayed version of that process where you have the rewire to same star version where you just choose uniformly an edge. And if it's disagreeing, okay, then you do what you know, what you're known to do, because you can just, okay, again, with probability beta over n, perform a voter model step, and with the other probability, you perform a rewiring. But if it's agreeing edge, you don't do anything. And this is just a time-delayed version of our process, right? And then, okay, the other process, so the dual sort of process that you want to consider is a continuous time walk on the graph, such that every directed edge rings at rate beta over 2n. And then, okay, there's this result. It's a bit of a tricky coupling construction, but basically it says that there exists a coupling between the continuous time random walk as defined here and the rewire to same time delayed version, such that if at a given time, which are basically the sum of the waiting times of this random walk, a random walker is happy, whatever that means. I mean, this one has to define, obviously. Then the opinion of that walker at time t is the same as the opinion of v started given at a different time point. So there's also this sort of duality relation where you can read off the opinion of one vertex by considering the random walk. This just as a side, or not as a side note, but it's not entirely defined. But the takeaway we want to get from that is that analyzing quantities of the continuous time random walk, such as, for example, mixing time and therefore spectral gap or Chiga constant, is helpful in our dynamic setting as well. And then I guess Deepening will start to talk about how to bound these quantities for that random walk.
What you get right.
Yes, yeah, everywhere edge the strings at that rate, and then you walk that rate, yeah. And there's a very particular coupling constructed of.
Okay, so as Max explained, so can you hear me? Yeah, so consider the initial graph Z0, which is just at the Shreni with parameters n comma half. And suppose you are in time t and your graph is gt at time t. So this is the evolved graph from GNP at time t. And this is obtained via oh, so is this okay? Is it visible or I should write bigger?
Yeah, you should write bigger. Yes.
Okay. Okay, so GT is obtained from Z0 by a voter model step with probability beta by n, and you take the rewiring step. Rewiring step with probability 1 minus beta by n. Right, now suppose you are in GT, then consider the random walk, just Max explained before that. So consider a continuous time random walk on GT, which is defined as, so whenever an edge, so suppose this is your graphical representation. So whenever an edge rings, so if the walker is on the starting point of the edge, he moves to the other point. And so each edge rings at rate beta by 2n. And if the edge rings, the walker just moves here. And now we want to understand the mixing time of this random walk in GT. And you can show that the mixing time of, so the stationary distribution of this walk is actually the uniform measure on GT. So if a walk mix before the two walker meets, then there is a high chance that they will eventually coalesce. So to understand the coalescing time, we have to understand the mixing time of this walk. And so the mixing time is generally obtained by the spectral gap. So P is a suppose P is a transition matrix of a Markov chain. With eigenvalues, let's say 1 equal to lambda 1 bigger than lambda 2, etc. Let's say lambda n. And then their spectral gap is defined as, so 1 minus lambda 2. Let's call it lambda. And then the mixing time, which is defined as minimum of t such that the total variation distance between pt and pi is less than equals to epsilon, where pi is a stationary distribution. Then t mix is upper bounded by 1 by spectral gap times log of 1 by pi minimum epsilon, where pi min is the minimum of pi. Oh, x belongs to the state space or something. Okay, so to understand the mixing time, we have to obtain a lower bound for the spectral gap. And to obtain a lower bound for the spectral gap, we use the Chijar inequality. So the Chijar constant, so consider a graph G. So Chijar constant of G is defined as, so minimum over S T such that S union T is the whole vertex set V and S and T are disjoint and mod of S is less than equals to N by 2. And you are taking minimum over NST divided by mod of S, where NST is the number of edges between number of edges with one endpoint in S and other in T. Endpoint in S and other in T. Okay. So we have to obtain a lower bound for this. And since this is a continuous time random walk with rate beta by 2n, we have to multiply this by beta by 2n. And you have to take, so ns of t, like at time t, what is the number of edges between s and t in gt, and also you have to consider yeah, number of edges in, so I should write it t. Okay, so this will be done via defining some stopping times here. Okay, so let us define L prime t, which is maximum over ST, such that ST are not too small, minimum of mod S comma mod t bigger than equals to some epsilon 2 times n, and you are taking NST of t minus half times mod S mod t divided by nt and maximum over in SS t minus 1 by 4 mod square divided by nt, where NSST is the number of edges in S at in the graph GT. So observe that and now define tau 2 prime is minimum over t such that L prime t is bigger than equals to 2 epsilon 3. So this stopping time actually controls the distance between the GT and the initial graph G0 via a cart S and T, where S and T are not too small, they are large in some sense. This is one stopping time. And next, let's define for UV in V, let MUVT is number of edges in the bond UV. Okay. Okay, so okay, let's take equal to 0. Okay, so if t equal to 0, that means you are at the Sreni with, so G0 is just at the Sreni with parameters in comma half. So your NST, which is number of edges between S and T. So you choose one point from S, that can be done by mod S, and you choose one point from T, that can be done via mod T, and each edge is present with probability half, so you get a half there. So this is the NST, and so that there is the expectation NST, expected NST, right? And then the Chijar constant NST divided by mod S mod T will be half times mod S, then just mod T by 2, and right, so yeah, so and mod T is, so mod T is n minus mod S, and mod S is less than equals to n by 2. So this is actually less than equal, bigger than equals to n by 4. And and the Chijar inequality says that the Chijar inequality says that the spectral cap of G is bounded below by Chijar constant divided by maximum degree, right? So we obtained a degree by maximum, just T max, and so this is bounded by n square by 4, and maximum degree is like np, so n by 2. So it's like, so it's like some constant time n, and probably yeah, you have to bound by, you have to multiply via beta by n. So there will be one beta by 2n. So here some constant times C1 times beta, and here also there will be 2 times beta. So there is beta square, and here it will be some 2 times beta. So yeah, beta by n. Okay, so H square is bounded by some constant time beta, and it is again bounded by D max is some constant times n times beta by n. So you will be get some constant times beta. So that should be the teacher inequality for the initial graph, and then using some stopping time calculation, defining appropriate stopping times, you you can also obtain a lower bound for the spectral gap of GT, and it is also it can be shown that it is also lower bounded by some constant times beta by defining appropriate stopping times. And the next idea is if you get this type of estimate at time t, so let's say you are here in time t, then we run the process for time t plus n square by Cn square by beta many steps, and our goal is to show that in this time the process has not changed substantially, has not changed substantially. That means you have a estimate for lambda gt at time t, and we can push this estimate to this time also, t plus Cn square by beta time, because in this n order of Cn square by beta time, the there cannot exist too many edges that are that will be rewired, and there cannot exist vertices which gain large degree. We can prove that, and from that the mixing time bounds and the consensus time bounds follows for large beta. Yeah, thanks. I have to say.
Thank you. Questions? Be silent. Yeah. Wait a minute.
The random walk that you're considering is the same that Max defined, right?
Max defined, right?
Okay.
Time random.
So somehow, I think I've forgotten the exact details. So only for large beta, do you know that the thing has not changed substantially, or even for small beta, any beta, you'll know that the graph has not changed substantially in that?
No, for large beta. So for large beta, this n square by beta. So the number of edges that can be rewired, it will be order of 1 by beta times. And then if beta is large, then it is small.
But the large beta case is harder to deal with than the small beta case, right?
Yeah, that is
Yeah.
harder, yeah, this part.
Yeah, that's why you have to do this.
Yeah, this type of estimates.
Just to clarify, so your lambda G of t is like at least beta,
At least
Right.
3 times beta.
and then that means your mixing time is of the order 1 over
1
beta.
over beta.
And presumably your pi is uniform on the graph, or
Uniform on the graph.
pi is uniform on the graph.
Yeah.
So that's of order log n, is it right? Or
Yeah, so I think we
that correct?
need some L2 concentration type of
I see.
estimate for the mixing time. So
Right.
this will not work for our case.
oh,
Yeah, this. Yeah.
Yeah, that's crucial, right? Because it's like you can sort of freeze the graph a little bit and start all over again. Okay.
the one contradiction there is that sort of I have is that beta large means that the graph also is changing quite a bit, right?
No. So rewiring.
No,
from
because the
is
beta
1
is the rate of the
beta.
voter model. Yeah, so if beta
Yeah.
gets very large, you will be very close to consensus. Further questions? Okay. Hmm? You have no remarks, so that has fallen through. Oh, after the second talk. I'm sorry for that. Okay. So thank you. We're done?
Yeah.
Yeah. Thank you.